Hello, this is Dr. Justin Glisan, the State Climatologist of Iowa for the Iowa Department of Agriculture and Land Stewardship. Today I'll be presenting Iowa weather, climatological trends, and impacts on growing conditions. Presentation highlights are as follows. We'll discuss the Iowa Observation Network, recent and long-term trends in both precipitation and temperature, precipitation extremes, their intensity and frequency, trends to projections, so where we've been, where we are, and what our trends are showing us, the impacts and effects of changing climate on the growing season, and then a discussion of climate outlooks that we can use as guidance moving forward for the planting season, for example. The first topic we'll discuss is the Iowa Observation Network. Now, the Iowa Observation Network is comprised of National Weather Service co-op stations, various stations at local airports across the state, and the civilian CoCoRaHS rain gauge network. What you are seeing now on the screen is a map of the National Weather Service cooperative or co-op observation station network across Iowa, denoted by the red symbols. You'll notice that there are clumps of observation stations around various parts of the state. Typically, there are more stations in and near population centers. Observations are usually taken at 7 a.m. and represent the previous 24-hour period. For example, rain totals taken at 7 a.m. today include all rainfall over the 24-hour period beginning at 7 a.m. yesterday. Other observations taken include the maximum and minimum temperature, precipitation type and amount, and at some stations, cloud cover, precipitation time of occurrence, and weather type. Regional and municipal airports also provide hourly observations, including relative humidity, wind speed, direction, and sustained gusts, among other fields. The next thing to note is that there are large swaths in which there are no stations. These are generally very rural areas. These gaps across the state do present some problems as we need to estimate and interpolate data within the gaps. This is particularly important in terms of precipitation. And let me define precipitation, as sometimes there are questions. Precipitation is any hydrometeor that falls from the sky: rain, snow, sleet, freezing rain, etc. Precipitation behavior is becoming more variable across the Midwest, including Iowa. So having a robust station network is of the utmost importance. To help fill in the gaps and expand the observation network, we rely on civilian rain gauge network called CoCoRaHS, or the Community Collaborative Rain, Hail, and Snow Network. Citizen scientists use a standard 4-inch gauge and report rain and snow totals each morning, typically at 7 a.m. Over the last year and a half, we have added over 140 new gauges across the state. In 2018, parts of southern Iowa endured a pretty substantial drought, with counties in southeastern Iowa experiencing extreme drought, or D3 conditions on a scale of D0 to D4. After holding multiple drought meetings with farmers, livestock producers, and ag stakeholders, and after working with ISU Extension, local cattlemen's associations, and other state partners, we've greatly expanded the network. The importance of this expansion is that it will give me more observations moving forward, as I use this data for drought and wetness monitoring. These observations are also important and can be used by county FSA offices for financial assistance in regions of extreme dryness or wetness. The goal moving forward is to have 2 CoCoRaHS gauges in each county, along with National Weather Service co-op stations. In my travels across the state, I often get asked, what is the difference between weather and climate, and how are they linked together? The next section of the presentation will discuss weather versus climate. Weather is the day-to-day state of the atmosphere. When we think about weather, we think about short-term variations from minutes out to a week or two. When we talk about weather, we often talk about conditions outside, such as temperature, humidity, precipitation, the amount of cloud cover, how far we can see to the horizon, and what the wind is doing. We talk about changes in the weather too. And when we do, we talk about what it means for the future. What should I wear outside? We ask ourselves, how hot or cold is it right now? What will it be like later today? And are we going to get any snow this week? Climate, on the other hand, is the weather of a place averaged over a period of time. And we often consider this time period a climate decade or 30 years. We choose 30 years as climatologists because it allows us to average out large-scale circulation features that impact weather in a given location. Things such as ENSO, which is the El Nino Southern Oscillation, other large-scale oscillations in the atmosphere, including the Madden-Julian Oscillation and Arctic Oscillation, that can impact the way the jet stream moves through the Midwest, impacts the storm tracks in wintertime versus summertime, things of that nature. Climate information includes statistical weather information that tells us about the normal weather expected at that given location. And it also shows us the range of weather extremes for a location. A great way to see the difference between weather and climate, and also how they are related, is looking at this figure. Those wiggles that we see represent a daily variation in temperature or precipitation. That straight line, the green line on the top, indicates climatology, or the average of the weather over that period. The second plot below that represents winter versus summer. Now in winter, we always expect colder temperatures and summer warmer temperatures. We do have spatial variation out seasonally. We can have warm periods during the winter time and cold periods during summertime. But typically, the ebb and flow of weather through the seasons averages out, and we have a seasonal climatology. Now that we know the difference between weather and climate and how they're interrelated, let's take a look at precipitation and temperature trends, which we pull from the observational record. I'll be showing you a set of plots going back to the historical record's beginning, 1895. And then I'll show you the last 30 years. And what you'll see is how things have changed over the last 30 years versus the long-term historical average. The first set of plots I'll show you are Iowa average temperatures since 1895. What these plots show you are the higher the peaks, the higher the annual temperature, lower the trough, the lower the annual temperature. So colder years versus warmer years. When we take the average of this behavior, what we've seen over the last 124 years is a 1/10 of a degree Fahrenheit increase per decade across the state. So we've seen a gradual warming across the state. What we see when we decompose the annual average temperature into maximum and minimum temperature is a pretty interesting story. Looking at the maximum temperature trend since 1895, what we see trend-wise is we haven't seen increase or decrease in the maximum temperature. We've effectively stayed the same. When we look at the minimum average temperature for the state of Iowa since 1895, we see something interesting. What we're seeing across the state is a 2/10 of a degree Fahrenheit increase per decade. Now, if you look at the time scale of 124 years, this would suggest that we've increased the temperature a little over 2 degrees since 1895. The next set of plots will highlight precipitation trends across the state. First, let me define precipitation as the total liquid equivalent of melted snow, sleet, ice, and hail combined with rainfall. When we talk about annual totals, we almost always talk about rainfall in the warm season, plus any kind of hail that might fall out of thunderstorms. In the winter, which is the driest season in Iowa, a majority of precipitation falls as snow or ice. The plot on the screen is similar to the annual average temperature, except now we are looking at the annual statewide precipitation going back to 1895. The higher the peaks on this plot represent the wetter years, while the drier years are the lower troughs below the trend line. The first of the two highest peaks over the last 124 years occurred in the Great Flood year of 1993, when over 48 inches of precipitation fell across Iowa. The second wettest year on record was 2018, when just over 45 inches of precipitation fell, just slightly less than 10 inches above average. Precipitation behavior is directly tied to the temperature of the atmospheric column by a relationship known as the Clausius-Clapeyron equation, which is rooted in physics. This relationship tells us that for any increase in atmospheric temperature, the water vapor holding capacity of the atmosphere also increases. A warmer atmosphere holds more water vapor and hence makes precipitation events more likely. Looking at the decadal trend since 1895, and given the increase in atmospheric temperature, precipitation across the state has increased by a little over 0.4 of an inch per decade, or nearly 5 inches more than fell in 1895. In the next figure, I'll draw your attention to the vertical axis, which represents annual average precipitation, and the horizontal axis, which represents years. Also of note are the red and green horizontal lines, the lengths of which represent an overlapping 30-year time segment since 1901. This figure is a different representation of how precipitation behavior has changed in a warming atmosphere across Iowa. Specifically, each segment represents a longer period as seen across the state. For example, the first time slice covers 1901 through 1930. The second segment covers 1911 through 1940, and this continues into the present decade, 1981 through 2010. The green line is the minimum precipitation threshold, or the floor of expected precipitation across Iowa in a given year. The red line is the maximum threshold, or the ceiling of expected annual precipitation across Iowa. You'll also notice yellow triangles which show the annual average precipitation scattered about the plot, above and below these red and green lines. We find that both min and max limits have been increasing since about 1930, highlighting that the state is becoming wetter. This behavior is in line with what is prescribed by the Clausius-Clapeyron relationship.
The next set of slides are similar to the long-term trend slides, except now we are examining the trends in temperature and precipitation over the last 30 years for the state of Iowa. This slide shows the statewide annual average temperature over the last 30 years. Of note are the peaks and troughs. The peaks are higher than the troughs. So what we have seen in the temperature behavior is the same as the long-term trend, though the temperature increase per decade has tripled. We now find an observed temperature increase over the last 30 years of 0.3 of a degree per decade, compared to 0.1 of a degree per decade going back to 1895.
The long-term trend going back to 1895 and the last 30-year trend show an increase in temperature and precipitation across the state. We are also seeing, in terms of extreme events, higher intensity events more frequently. So instead of these gentle rainfalls that we have over a few hours, we're getting 2 to 3 inches over 3 to 4 hours. If we break down the trends into seasons, what we've seen over the last 30 years is that seasonal spring rainfall is shifting earlier in the season, and it's also increasing. When we get into fall, we're also seeing more pronounced, heavier rainfall events, especially late September, early October. Right in the middle, during summertime, we're seeing rainfall decline, which is right around the time crop and livestock need them the most because it's the warmest time of the year. In terms of the growing season, it is striking that we are seeing a seasonal shift. So when we want to start field work in the springtime, we're seeing rainfall increase. And then when we want to start harvesting, we're also seeing increased rainfall as we did in 2018 and 2019. These are the climate trends that we need to monitor the most, given the agricultural nature of the state. Precipitation extremes will be highlighted in the next section. We'll be talking about their aerial coverage, where they're occurring, the frequency at which they're occurring, and how we've seen a change over the past few decades. Let's first consider what a precipitation extreme is, and we'll define this by typical behavior at our National Weather Service co-op stations across the state of Iowa. So typically a co-op station will experience 1 or 2 days with a 24-hour event of 2 inches or more annually. These are what we consider the 99th percentile or an extreme event, so they don't happen often. What we've seen over the last 2 decades is that these events are becoming more numerous and more intense. So both the spatial scale, the time scale in which they fall, but also how fast they fall. And of course, the rapidity at which a precipitation event occurs will have impacts on a variety of different landscapes. If we look at urban and suburban stormwater, these higher intensity events are not able to soak into soil. So they run off into our sewer-based infrastructure. Now, a lot of this infrastructure is old, and moving into a regime in which we're seeing higher intensity precipitation events, the sewer systems can't keep up with this type of flow, so we get flash flooding. Also of major concern, given the agricultural extent of the state, is soil runoff and soil loss. When you get into these higher intensity precipitation events, you get a lot of water dumped onto bare fields, for example, which will pull off soil at the surface. This also has an impact on nitrate loss for fertilizers that have been applied to soil. And then in general, looking at the state, looking at our basins, to our west we have the Missouri Basin, and to our east we have the Mississippi Basin. Now, with runoff events becoming higher intensity and also upstream, so north of us, more water, more rainfall, more precipitation, more melt occurring in wintertime is producing larger scale downstream flooding. And this was of particular note given the historic nature of the flooding event that we had in southwestern Iowa in March 2019. We had a setup of anywhere from 3 to 5 inches of melted snow plus rainfall on top of that running into the Missouri Basin system over 20 to 34 hours. Given the amount of water flowing into the stream system and into the Missouri Basin itself, we had the Spencer Dam in Nebraska destroyed, and we had record, again, flooding in southwestern Iowa that cut a lot of fields with silt and debris, and this impeded planting for the farmers in that region. And we don't expect, given the historic nature of that flooding, for farmers to plant down in that region for many years. These are things that we have to take into account given the trends that we're seeing in precipitation intensity and frequency. Let's now take a look at how the frequency of precipitation events over 24 hours has changed over the last few decades. Let me explain the components of the graph, and then I'll describe what's going on. This is a precipitation frequency versus intensity plot for central Iowa. Basically, how often a given amount of rain falls over a 24-hour period. The vertical axis is the frequency, or how often a given event occurs. The horizontal axis gives us the range of rainfall. The blue bar represents the historical record going back to 1895, while the red bar is the last 20 years. If we take the pool of all rainfall events that have occurred, historically, a little over 89% of the time, central Iowa has experienced what we would consider a light rainfall, generally under an inch. These are the types of rain that are able to soak into the ground. If we look at these gentle events over the last 2 decades, we notice a little over 1.5% drop in these lighter rain events. What this indicates is a shift in the frequency of rainfall events to the heavier end of the spectrum. In fact, if you look at all the thresholds to the left of the first set of bars, the frequency of these events has increased over the last 20 years. Let me draw your attention to the very last threshold to the right, the 3+ inch events over 24 hours. While these events represent only 0.01% of all rainfall episodes historically, over the last 20 years, these events have increased threefold. One recent example that stands out is the Ankeny event, which occurred from June 30th through July 1st in 2018. Over a 3 to 4 hour period, anywhere from 6 to 8 inches of rain fell across central Iowa. At my house in Des Moines, in my CoCoRaHS rain gauge, I received a little over 5.5 inches in the same period of time. Widespread urban flooding was reported across Des Moines into northern Polk County. Again, while these events are extreme and do not occur anywhere near the frequency of lighter precipitation events, we have seen a marked shift towards higher intensity events over the last few decades. Now that we've seen trends in both temperature and precipitation, and the trends that we're seeing specifically for extreme precipitation, let's look out into the near future and see how these trends project out. We'll talk about challenges moving forward, changes in precipitation across the state, and also temperature changes that will affect conditions on the ground, such as drought, the growing season, things of that nature. Now, in a changing climate, we do see challenges moving forward, especially for agricultural states. What we've been seeing is increasing variability in the weather during the year. So longer heat waves, longer cold snaps, the hots are getting hotter and the colds are getting colder. And this ties in with the increasing nature of temperatures across the effectively much of the United States and the mid-latitudes. We're also seeing, and we kind of discussed this earlier, increases in annual precipitation and greater extreme precipitation. Also, we have seen in the trends a shifting of the seasonality in precipitation. Again, we're seeing more rainfall earlier in the spring, and we're seeing more rainfall during the fall months, especially end of September, early October. What we've also seen is drier conditions in summertime. Effectively, after the first or second week of July, we get into an extended period of below average rainfall, and we've seen this in the trends going back a few decades. Given that we have an increased amount of water vapor availability in the atmosphere, we are also seeing an increase in low-level humidity. Low-level humidity will increase stress on livestock. It'll give us a higher probability of having more rainfall events, given that there is low-level moisture available for any type of transient system that moves through the state. Think about summertime. You get a stationary front or some sort of frontal boundary that sets up over the state. With this pool of low-level moisture and humidity, conditions are favorable for overnight convection or thunderstorms forming overnight if the proper forcing is there. We're also seeing an increasing amount of, or rather an increasing demand in the atmosphere for water. So we're seeing sources and sinks set up, lower level moisture, and we're seeing a differential through the atmosphere of water vapor. And then in general, we're seeing more extremes in all the weather variables. So if we think of temperature, again, we've talked about a warming nature in the atmosphere. But again, we're also seeing colder temperatures persist longer, warmer temperatures persist longer. In terms of warmer temperatures, when you have a persistence in these warmer temperatures in the summertime, you get into the increasing probability of flash drought conditions. So drought popping up faster than normal. Typically, drought would form over a season. With higher temperatures over a longer period of time and the lack of precipitation in summertime, flash drought can form in weeks. So these are things that we have to take into account. Let's first look at future precipitation changes. What we'll look at are observed changes that we've seen since 1895 across the United States and regionally. And then we'll look at seasonal projections and changes that we see moving into the end of the 21st century. Combined with this, we'll also look at changes in precipitation extremes, where they occur, how often they occur, and the intensity at which they occur. What this plot is showing is the percent of observed U.S. precipitation change. Now it's split up by region, and you see those bars for each of the regions. The greener the bar, or the higher the percent change in precipitation we're seeing. On the reverse, the browner the bar, or the lower the bar dips, the less amount of precipitation we're seeing. As you can see across much of the Midwest and the central part of the United States, we've seen an increase in precipitation since 1895. And if we consider Iowa, or the general region around Iowa, including Iowa, we've seen anywhere from a 10 to 15% increase in the amount of precipitation we're seeing. Now, again, this does betray that we are seeing a seasonal shift in rainfall. Again, we're seeing drier summer times and then wetter falls, wetter springs. So we're shifting when rainfall is occurring. You'll also notice there's speckling across the upper Midwest. We're seeing pockets of above 15% increases in precipitation. So we are seeing localized changes in where rainfall is falling, and this impacts the growing season. This impacts planting row crops, planting specialty crops, planting flowers in your backyard. Combined with the increase in temperature, we do project out that we will see a seasonal shift increase in seasonal intensity increases for 3 of the months, or rather 3 of the seasons. Now that we've looked at trends in precipitation, let's take a brief look at projected changes. These projections are based on climate modeling and are taken from the 4th National Climate Assessment produced by the federal government. A changing climate affects more than just temperature. The location, timing, and amount of precipitation will also change as temperatures rise. Maps show projected percent change in precipitation across each season for 2071 through 2099 compared to the baseline period of 1970 to 1999 under an emissions scenario that assumes continuing increases in emissions. Teal color indicates precipitation increases, while brown represents decreases. Striped or hashed areas indicate that the projected change are significant and consistent among models. White areas indicate that the changes are not projected to be larger than could be expected from natural variability. In general, the northern part of the U.S. is projected to see more winter and spring precipitation, while the southwest U.S. is projected to experience less precipitation in the spring. Wet regions are generally projected to become wetter, while dry regions become drier. So we're seeing extremes lock in on either side. Summer drying is projected for parts of the U.S., including the Northwest and the southern Great Plains. When looking at Iowa, especially in winter and spring, we are seeing that hatched area, or the stripes, moving into the state. This suggests that the models used in the Global Climate Model Ensemble are in agreement that we should expect increased wintertime and spring precipitation. If we look at fall, we don't see that striping area, but we do see that there is a probability of having wetter conditions. And then we look at summer. Summer, the projection across much of the United States is for a decrease in precipitation. And we have seen some semblance of this over the past 30 years as our seasonality has shifted. Now that we have looked at the projected seasonal behavior of precipitation, I will now discuss projected changes in daily extreme precipitation events through the seasons. And this is through the lens of a 20-year return period. A return period is the length of time that we would expect a particular intensity event to occur once. So, for example, a 20-year return period indicates that a 24-hour event of X intensity should occur only once in 20 years. Extreme precipitation events occur when the atmosphere is near saturation. Hence, extreme precipitation events are generally observed to increase in intensity by about 6 to 7 degrees for each degree Celsius or 1.8 degree Fahrenheit increase, as dictated by the Clausius-Clapeyron relationship. Again, the Clausius-Clapeyron relationship tells us through physics that any increase in temperature in the atmosphere necessitates an increase in the water vapor holding capacity of the atmosphere. The figures on this slide show the projected change in the 20-year return value for a one-day precipitation total for the mid-21st century, which is shown on the left, and the late century, which is shown on the right. Under both emission scenarios, in an emission scenario is how much greenhouse gas is being pumped into the atmosphere, all regions within the United States are projected to see increases in higher intensity events. When focusing on Iowa, the climate model projections show an increase of anywhere from 10 to 15% from mid to late century for the lower emission scenario, and at the most extreme, over 15% and up to 20% under the high emission scenario at the end of the 21st century. As we did with precipitation, now let's look at future temperature changes. We'll first look at observed changes that we've seen since 1895, again across the United States, regionally, and then impacts on Iowa. Then we'll look at growing season implications on a warming atmosphere, along with impacts on agricultural productivity across the United States and specifically in Iowa. This graphic shows the observed temperature change in degrees Fahrenheit across the United States since 1895. The darker the red, the warmer the temperature has become. Likewise, darker blues indicate a negative temperature change, or that temperatures have become cooler. As you can see, a majority of the United States has seen a temperature increase, with much of the northern tier of states experiencing increases greater than 1.5 degrees Fahrenheit. Alaska has seen the largest positive temperature changes, as the high latitudes have experienced warming at double the rate of the lower latitudes. This phenomenon is known as Arctic amplification. Across Iowa, we've seen anywhere from a half degree increase to 1.5 degrees in some locations. Also of note are the embedded bar charts showing decadal increases for the United States average temperature, as well as various geographical regions. What's been consistent across much of the United States is that the highest temperature increases have occurred in the last few decades, including the Midwest. The frost-freeze season length, defined as the period between the last occurrence of 32 degrees Fahrenheit in the spring and the first occurrence of 32 degrees Fahrenheit in the fall, has increased in each United States region during 1991 to 2012, relative to the time period between 1901 and 1960. Increases in frost-free season length correspond to similar increases in growing season length. Across Iowa, we've experienced on average an increase in the growing season of 9 days. Having a buffer of extra days could be beneficial if spring planting is delayed, as was seen in 2018 and 2019, or if there are similar delays in fall harvest, both seen in the last 2 years as well. One thing of note is the dwindling nature of summer rainfall, as was discussed earlier. Even with an expansion of the growing season, increased precipitation in early spring and fall may produce a mixed bag given the increased variability of precipitation events over the last few decades. Specifically, and as we have kind of discussed earlier, When we have earlier precipitation events in spring, and then we have precipitation events of higher intensity during the fall, and a deficit of rainfall during maturation, both in crop and when livestock are coming along, we see episodic periods of wetness and even drought that will impact growing season moving forward. So these are things we have to take into account, given that we are seeing an increase in the growing season. We are seeing more impediments being thrown at us, given the nature of weather variability across the Midwest and Iowa. Okay, on to the next slide, which is somewhat similar to the previous slide. However, we are now looking at more data from the 4th National Climate Assessment Report released last year. These 4 figures are based on GCMs, or again, global climate models that produce numerical projections into the late 21st century. The general theme here is the projected changes in key climatic variables that impact productivity in the agricultural sector. For Iowa, these impacts include row crops such as corn and soybeans, but also specialty crops including fruit, nuts, and cover crops. Again, these cover crops can be used for livestock feed, but also as a system to lock in soil as we are moving into a pattern of higher intensity rainfall events. These key variables are all tied to the projected increases in surface and atmospheric temperatures. We have already experienced changes in these fields over the last decades, but with increases in population and emissions, some GCM projections indicate significant changes in the future. The top 2 plots show changes in frost-free season length on the left, and on the right, changes in the number of frost days across the United States. The 2 fields go hand in hand in that an increase in the length of the frost-free season is directly correlated to the decrease of frost days. What we're seeing across the country is a significant increase in the frost-free season, and by proxy, an increase in the growing season. And we have also seen this over the last few decades, given our trends for a warmer atmospheric temperature. The projections for the end of the 21st century show 30 to 40 additional frost-free days across Iowa. We see this signal reinforced by a similar decrease in the number of frost days across the state. The 30,000-foot view of this suggests what our recent trends are showing us. Increased atmospheric temperatures will continue to expand the growing season across much of the state, though we will see seasonal impacts given the seasonal shift of precipitation that we've seen projected out into the future. The bottom 2 figures also indicate that the number of consecutive dry days will also increase across much of the United States. Now, when we talk about dry days, we're talking about days in which precipitation has not fallen, but also we're seeing an increase in surface temperature, so the heat of the day. Increasing the length of a dry spell, especially in summertime, will increase the probabilities of heat waves as well as drought, as the summer signal for dryness is strongly tied to higher temperatures. This type of behavior, along with a number of hot nights, will have a drastic impact on crop and livestock stress.
Now we'll talk about, in summary, the changes that we've seen in the climate system and how they will impact things moving forward. First, and the broadest point here, is global mean temperatures will continue to increase throughout the 21st century if CO2 concentrations continue to increase. Now, CO2 is the dominant radiative forcing gas in the atmosphere, but we have other greenhouse gases that will also impact the amount of warming that we see in the atmosphere and near surface. Another important thing to note is that these temperature changes will not be uniform across the globe. And where we'll see market increases are over land surfaces, as opposed to increases over the ocean. Now, yes, we will see more solar radiation input into the oceans, especially in the Arctic, as we get into further decline in sea ice. but the dominant signal will be for increases in temperature over land surfaces. And as we see global temperatures increase, we'll see hotter extremes. Now, hotter extremes meaning warmer temperatures, but also warmer temperatures for a longer duration, more days in which we see hot temperatures. And this includes temperatures overnight, where we've seen a pretty substantial increase in overnight temperatures. On the reverse side of this, we'll also see fewer cold days or cold extremes on the daily scale and also the seasonal time scale, because we are seeing a warming surface temperature, a warmer atmospheric temperature, but also warmer seasons, especially in wintertime. As we look at precipitation behavior, we will see increases in precipitation given the increasing global mean surface temperature. So again, this goes back to our Clausius-Clapeyron relationship, in which a higher temperature necessitates more water vapor holding capacity in the atmosphere. And where we see these precipitation increases are related to the amount of warming that we see in the atmosphere. So globally, we could see anywhere from a 1 to 3% increase in precipitation per degree Celsius. One thing of note, though, is that we'll see substantial spatial variation in these changes. So when we talk about spatial variation, we talk about where the precipitation is actually falling. Now, we've seen in the global climate model projections that there are parts of the United States, specifically the monsoon region in Arizona, in which we'll see decreases in seasonal rainfall. But we also see across Iowa and across much of the United States in summertime a decrease in the amount of rainfall occurring. And where we see this shifting is into the early spring and into the fall, especially over Iowa in the Midwest. What we are seeing are that wetter parts of the globe, wetter parts of the United States are getting wetter. And then we get into a situation where drier parts of the United States, drier parts of the state of Iowa, where southern Iowa specifically, are getting drier. And these are locked into the way that the jet stream has behaved over the past few decades, given the decreased temperature gradient between the higher latitudes and the mid latitudes. One final thing to note, annual surface evaporation will increase as the temperatures increase. So you have a higher temperature at the surface, a higher temperature in the atmosphere. We're able to hold more water vapor at the surface, more water vapor in the atmosphere. We'll see more of this evaporation given the positive feedback loop that is related to temperature and water vapor. Over land, evaporation will be linked to the amount of precipitation that falls. So yes, we have subsoil moisture and we have subsoil capacity for moisture to be held. But over land, the dominant signal that we're seeing is that in regions where precipitation is more likely to fall, we'll have a higher probability of more evaporation, since that water vapor is available in a warming atmosphere. Evaporation over land is important because it is linked to crop evapotranspiration, or physiological processes during crop maturation, but also livestock stress. When you have an increase in evaporation at the surface, you're losing water vapor at the surface. You can get into periods of long-term dryness that can impact the way that livestock feed, the way that livestock go through their life cycle. So yes, when we talk about the surface balance of precipitation versus evaporation, we need to take into account the physiological processes of both animal livestock and also of crop, whether specialty or row crop.
The final section of the presentation will highlight climatological products that can be used as short and long-term guidance for agricultural applications. Many of these products are issued by the Climate Prediction Center, or CPC, which is housed under the National Oceanic and Atmospheric Administration. CPC issues numerous products, including short and long-term probabilistic temperature and precipitation maps, 8 to 14-day U.S. hazard maps that show the probability for hazards such as heavy rain and snow, as well as temperature extremes, along with other experimental products. Drought information, including monthly and seasonal outlooks for the United States, is also updated monthly. On the more technical side, CPC issues ENSO forecast, which is the current phase of the El Niño Southern Oscillation, or ENSO. You probably know ENSO under the name El Niño, which is the warm phase of the oscillation. La Niña happens to be the cold phase. If a phase of ENSO is present, specific meteorological impacts tend to occur for a longer term period. For example, if El Niño is present during late fall and persists into winter, Iowa typically experiences a warmer winter season. I will also show you other products from institutions such as the Midwestern Regional Climate Center that highlight seasonal planting products, such as the Growing Degree Day Calculator and Frost Freeze Impact Maps. As I go through the next set of slides, I will show different products and explain how they can be interpreted. Here's the first of the two short-term outlooks that CPC releases. The plots are all probabilistic, meaning that they give us a probability of temperature and precipitation behavior over a given time period. These are the 6 to 10-day outlooks, which are issued daily just after 2 p.m. Central Time. The outlooks give us an idea of expected conditions 1 week out. So typically at the end of the 7-day forecast you see on the morning or nightly news. The plot I'm showing is valid 6 to 10 days from today. The plot on the left of the figure is temperature with the color scale below. The deeper the blue, the higher the probability of colder than average conditions. On the flip side, the deeper the red, the higher the probability of warmer than average conditions. Where gray is shown, climatological behavior, or what is expected for this time of year, is expected. What we are seeing from these outlooks are very high probabilities of unseasonable warmth and a similar signal for precipitation. Looking at the precipitation color scale, the deeper the browns, or the darker the browns, the higher the probability of an area experiencing drier than normal conditions. Likewise, the deeper the green color, the higher the probabilities that that given region will experience wetter than average conditions. The second short-term product is the 8 to 14-day outlook, which is valid a week and a half out from today and goes out to 2 weeks. This product is also released at 2 p.m. Central Time every day. We are seeing similar behavior in what is shown in the 6 to 10-day outlook. These two products are snapshots in time. But if you examine the trend through each snapshot or each daily release, you can get an idea of how the weather pattern is shifting. This 3 to 4 week outlook is somewhat of a bridge from the short-term outlooks to the monthly outlooks. These outlooks are typically issued every 7 days and provide guidance for temperature and precipitation towards the end of a 30-day period. One thing to note is that the temperature outlook is operational while the precipitation outlook is still experimental or going through experimental research. These outlooks, as with all other outlooks, are based on departures from the 1981 to 2010 base period, or the current climatological decade. These are 2-category outlooks and differ from the official current 3-category outlooks used for the monthly and seasonal products. The shading on the temperature map depicts the most favored category, either above normal, depicted as A, or below normal, depicted as B, with the solid lines giving the probability, greater than 50%, of this more likely category above or below. So what we're getting is a probability of A or a probability of B. The shading on the precipitation map depicts the most favored category, either above median, which is A, or below median, which is B, with the solid lines giving the same probability as in the temperature, greater than 50%, of this more likely category, above or below. In areas where the likelihood of a 2-week mean temperature and accumulated precipitation amount are similar to climatological probabilities, equal chance, or again, EC is indicated. Remember, EC is a 33% probability of above, 33% probability of below, and a 34% probability of climatological behavior. As you can see from the plot of temperature, the shaded area is that area above 50% probability of having above average temperatures in the 3 to 4 week timetable. We see EC on the West Coast, so we're not getting a lot of robust guidance in terms of temperature behavior there. Looking at the precipitation plot, we're seeing that area of greater than 50% for below average precipitation behavior stretching from California all the way to the Great Lakes. And then we have that green area along the mid-Atlantic states to Texas, and then the panhandle of Alaska. In between those two regions, we see EC. So what we're showing here in the experimental product is that over the state of Iowa, within the 3 to 4 week timetable, we're trending towards drier than normal conditions in the probabilistic models, and we're trending above average for temperature behavior. And this is moving us into the first part of January 2020. The final two slides show the longer-term climatological outlooks produced by the CPC, the first of which is the monthly outlook. There are two issuances of these outlooks, the first of which occurs on the third Thursday of the month. For example, the initial or half-month lead outlooks for January are issued on the third Thursday of December. The final outlooks are then released on December 31st and are valid for the month of January. The color scale is the same as the short-term products with one exception. In regions where outlook probabilities are too low to make a significant determination, EC, or equal chance, is used. As with the 3 to 4 week outlooks, EC means equal chance of above, below, or near average behavior, with a slightly higher probability at 34% towards near average conditions. The current interpretation of the half-month lead outlooks for January 2020 indicates slightly elevated chances of colder than average conditions for extreme northern Iowa, basically along the Iowa-Minnesota border, as denoted by that light blue color. EC conditions prevail for the remainder of the state and much of the country. We continue to have a lack of guidance for precipitation, as we saw in the earlier products. As a reminder, in winter, the phase of the El Niño Southern Oscillation climate signal typically influences temperature and precipitation behavior. The neutral phase of ENSO is currently in place, and hence, in the absence of an El Niño or La Niña signal, long-term climatology and recent trends become the dominant seasonal predictor. Other climate patterns are also considered, such as the phase of the Madden-Julian Oscillation, MJO, and the Arctic Oscillation, AO. A negative phase of the AO produces shifts in the storm track across the Midwest, along with colder air masses. A positive AO shifts the storm track further north and generally keeps colder air out of the region. The CPC does not produce a snowfall outlook for winter or in general because these systems are extremely variable and are often not predictable more than a week out. The final long-term climatological products from the CPC are the seasonal outlooks, which span a 3-month period. These outlooks are typically issued on a mid-month Thursday. The given lead time for the current outlook is 2 weeks, or a half-month lead, which is similar to the monthly products, but also go out a full year. So the current longest-term product is the 12.5-month lead, January, February, March 2020 outlook. Looking at the JFM 2020 outlooks, we are seeing a more robust signal for elevated chances of wetter than normal conditions across much of the upper Midwest, including Iowa. Temperature-wise, slightly higher probabilities of colder than average conditions are shown across northern Iowa. These signals are also reflected in the February, March, April outlooks, which are currently at a 1.5-month lead. Moving through winter into spring, we are always mindful of agricultural impacts with a particular focus on moisture variables, including precipitation and subsoil conditions. Modeled subsoil moisture is near capacity currently as we end 2019, anywhere from the 90th to 99th percentile. If you think of a sponge, current conditions indicate the sponge is almost soaked with a moisture infiltration capacity of anywhere from 1 to 10%, depending on where you are in Iowa. Right now, northern Iowa is the wettest part of the state, with southeastern Iowa the driest. Also of particular interest in winter is the snowfall that is received in the upper Missouri and Mississippi basins. Given that stream flows are currently near or above average, flooding conditions could be an issue in spring if we do see above normal snowfall across the upper Midwest. Another great tool that can be used in terms of planning when to plant or to cover at-risk plants from potential early freeze is produced by the Midwestern Regional Climate Center. The tool uses climatological observations over a 30-year period from stations compiled around the Midwest. The tool plots a date range for the average first freeze at 2 temperatures. Looking at the slide, the plot on the left is the median first 32-degree freeze, while the plot on the right is the same, but for 28 degrees, which is the killing freeze, which ends the growing season for most plants and crops. One question that we often ask ourselves is how far out seasonally can frost be predicted? Typically, the second or third week of September is when climatologists and atmospheric scientists start to get a handle on two things. The first of which is the short-term climatological temperature outlooks, so moving out 2 weeks. And then the actual meteorological temperature forecast going out 7 to 10 days. These are the forecasts of highs and lows that you see on the nightly news. Any notion that frost prediction can be done before mid-September is without scientific merit, especially 2 seasons out. Trend-wise, what we've seen over the last few decades is that these frost dates are moving further into the fall season. And we've seen this with a warming fall temperature trend over the last 30 years. Looking at the plot on the left, the first average 32-degree freeze, what we're seeing generally across the state of Iowa is that we're seeing a freeze occur during the first part of October. Some pockets in northern Iowa are seeing that first 32-degree freeze towards the end of September. When we look at the first hard freeze at 28 degrees or below, climatologically what we're seeing is across the northern part of the state, anywhere from the 1st to middle of October, and then in the southeastern part, southern central part of the state, end of the month, end of October. So these give us a good idea of when we would climatologically see the first 32-degree freeze and then the hard frost at 28 degrees. The final slide here is the slide for the website of the Iowa Department of Agriculture and Land Stewardship's Climatology Bureau. On this page, you'll find a variety of tools that can be used in agricultural applications. You'll find recent climatological maps, monthly weather reports that I submit at the end of each month, historical weather reports going back multiple years, weekly growing season reports during the growing season that are specifically targeted at row crops, but also give a weather summary for the state. Current conditions, including soil temperature, soil moisture, precipitation and temperature behavior, things of that nature. And then finally, climate outlooks from the Climate Prediction Center, as well as drought monitoring. Thank you for viewing my presentation. Below is my contact information, my email address, and office telephone number. Please feel free to contact me if you should ever have any questions about Iowa climatology or just weather and climate in general.